This question looks at reactions of hydrogen peroxide and of cobalt-2 ions. Part A. Aqueous hydrogen peroxide decomposes as shown in equation 2.1. The reaction is catalyzed by manganese 4 oxide, MnO2. A student investigates the decomposition of a hydrogen peroxide solution as outlined below. 1. The student adds 50 centimeters cubed of H2O2 aqueous to a conical flask. 2. The student adds a small spatula measure of MnO2 and quickly connects the flask to a gas syringe. 3. The student measures the volume of oxygen every 200 seconds. Part 1. Process the results as outlined below. 1. On page 5, plot a graph of volume of O2 against time. Use your graph to find the rate of the reaction in centimeters cubed per second at t 500 seconds. Show you're working on the graph and in the space below. So firstly, what I've done is I've written a scale for time and the volume of O2. Next, we need to plot the results. So 0, 0 is our first point, and here we mark it with an X. Then we have 215, again marking with an X, 428, and then 636, 841, 1046, 1200 and then 48, and 1400 and then 50. So here I have plotted all of the points that we have been given in the results table. Next, we need to draw a curve of best fit. So a curve would be connecting all of the points because they form a curve rather than a line of best fit. The next part of the question, we're asked to find the rate of reaction in centimeters cubed per second at t 500 seconds, which means we need a tangent at t equals 500 seconds. So drawing a tangent at t equals 500 seconds using a ruler, we draw a straight line at t equals 500 seconds, like so. Then, to work out the rate of reaction, we need to work out the gradient of the tangent. So working out the tangent, if we take point 40 on the tangent and follow it down to the x-axis, we get 700. And then taking point 20 on the tangent, following this down, we get 0.180. So working out the tangent is the change in y over the change in x. So that would be 40 minus 20 divided by 700 minus 180, which gives us a rate of reaction of 0.038 centimeters cubed per second at t equals 500 seconds. Writing this on the answer line. To get the 5 marks for this question, you get a mark for correctly labelling the graph and having a sensible scale. You get a mark for plotting the points correctly, a mark for drawing a curve of best fit, a mark for plotting the correct tangent at t equals 500 seconds, and a mark for the correct calculation of the gradient of the tangent, 0.038 centimeters cubed per second. Part 2. The student allows the reaction in equation 2.1 to proceed until no more gas is evolved. The volume of O2 in the syringe is now 55 centimeters cubed, measured at room temperature and pressure. Calculate the initial concentration of H2O2. Give your answer to 2 significant figures. Firstly, I've copied over the key pieces of information from part 1 that we're going to use to answer part 2. Then we need to highlight the other bits of information we're given in part 2 that we can then use to answer the question. Firstly, we're told the gas volume of oxygen is 55 centimeters cubed and that it's measured at room temperature and pressure. So we're going to be using the equation volume over molar volume, which in this case, because it's centimeters cubed, will be 24,000 centimeters cubed, equals moles. Then we're told that we need to work out the initial concentration of H2O2, and we need to give our answer to two significant figures. We can use this equation to work out the number of moles of oxygen. So that would be 55 divided by 24,000 gives us 2.29 times 10 to the negative 3 moles of oxygen. Then looking at the molar ratio of the equation, we have a 1 to 2 molar ratio. So that means we need to take the number of moles of oxygen, 2.29 times 10 to the negative 3, and multiply them by 2 in order to get the number of moles of hydrogen peroxide. So that would be 4.58 times 10 to the negative 3 moles of H2O2. Then we're working out concentration. So we're going to use the equation triangle N over V times C. So that would be number of moles, 4.58 times 10 to the negative 3 divided by 50 times 10 to the negative 3, because we've taken volume, or 50 centimeters cubed, converted it to decimeters cubed, which gives us a concentration of 0.092 moles per decimeter cubed, which we can then write on the answer line. To get the marks for this question, you get a mark for working out the moles of oxygen, a mark for working out or factoring in the molar ratio, so multiplying the moles by 2 to get the moles of hydrogen peroxide, and then you get a mark for working out concentration and giving your answer to two significant figures, 0.092. Part B. Hydrogen peroxide can act as an oxidizing agent or as a reducing agent. Some standard electrode potentials are shown below. Use this information to write an equation for a reaction in which hydrogen peroxide can act as a reducing agent. The key words in this question are reducing agent. That means that hydrogen peroxide is going to be oxidized in the overall equation that we create. So that means we're going to use the equation or the electrode potential featuring hydrogen peroxide with the lower electrode potential. And that means that our other electrode potential will need to be reduced, and we're going to use manganese. So the electrode potential with the second highest value, but it's higher than the electrode potential for hydrogen peroxide. And what's going to happen is its oxidation number in manganese will shift from +7 to 2+, and therefore will be reduced, whilst hydrogen peroxide is being oxidized. So what's going to happen, because hydrogen peroxide has a lower electrode potential, its equilibrium is going to shift to the left, whilst the manganese electrode potential is more positive, so it will shift to the right. So rewriting these equations, we would have H2O2 goes to 2H plus O2 plus 2 electrons, and then MnO4 minus plus 8H plus 5 electrons goes to Mn2 plus 4H2O. Next, we need to scale our electrons. We do this by making sure that they're the same number. So we would have to multiply our hydrogen peroxide equation by 5 so that we get 10 electrons, 5 oxygens, 10 H pluses, and 5 hydrogen peroxides. And then we multiply our manganese equation by 2 so that we get 10 electrons and 2 MnO4 minuses, 16 H pluses, 2 Mn2 pluses, and 8 waters or H2Os. So writing the overall equation, we would have 5 H2O2 plus 2 MnO4 minus plus 16 H plus 10 electrons goes to 10 H pluses plus 5 O2s plus 10 electrons plus 2 Mn2 pluses plus 8 H2Os. Next, we can cancel out some aspects of this equation. We can cancel out the electrons first, and then we can cancel out some of the H pluses. We can cancel out all of the 10 on the right hand side, and we can cancel out 10 on the left hand side, so we're left with 6 H pluses. Therefore, making our overall equation 5H2O2 plus 2MnO4 minus plus 6H plus goes to 5O2 plus 2Mn2 plus 8H2O. To get the 2 marks for this question, you get a mark for balancing the 2 equations, so scaling the electrons and making sure that they're both 10, and then you get a mark for the correct overall equation. Part C. Cobalt-2 forms complex ions with water ligands and with chloride ligands. With water ligands, cobalt-2 forms a pink octahedral complex ion, COH2O6 2+. With chloride ligands, cobalt-2 forms a blue tetrahedral complex ion. A student dissolves cobalt-2 sulfate in water in a boiling tube. A pink solution forms. Experiment 1. The student places the boiling tube in a water bath at 100 degrees Celsius. Concentrated hydrochloric acid is added dropwise. The colour of the solution changes from pink to blue. Experiment 2. The student places the boiling tube from experiment 1 in an ice water bath at 0 degrees Celsius. The colour of the solution changes from blue to pink. Part 1. Write the equilibrium equation for the reaction that takes place when the colour of the solution changes. So this question is asking about a ligand substitution reaction. So we're reacting copper 2 with water ligands. So that can be written as COH2O6 2+. And we're told in the question that we're forming a tetrahedral complex. So that means we're going to react with 4 chloride ions because it's a tetrahedral complex with chloride ligands. So 4 chloride ions. And then the equilibrium would produce COCl4, because that's our tetrahedral complex, 2- plus 6H2O. To get the mark for this question, you must have the full complete equilibrium. Part 2. Explain the observations and predict whether the formation of the blue colour is exothermic or endothermic. The first statement we can make is that the equilibrium shifts depending on temperature, but we need to be a little more specific and say that the equilibrium shifts right at 100 degrees Celsius, which we're told in the question because at 100 degrees Celsius the colour changes from pink to blue, which means it's going from COH2O6 2+ to the blue tetrahedral complex ion, or COCl4 2-. And therefore that means that the enthalpy change for this equilibrium is endothermic and not exothermic. To get the 2 marks for this question, you get your first mark for stating that the equilibrium shifts right at 100 degrees Celsius. Alternatively, you could say that the equilibrium shifts left at 0 degrees Celsius. And then your second mark comes from saying that it's endothermic.